let's look at a real data set. It's called the Keeling Curve because the name of the scientist who started collecting it way back in 1958 was someone Keeling. He has since passed away, but I think his son has kept collecting it, so it's still called the Keeling Curve. It's the amount of carbon dioxide in the atmosphere measured somewhere in Hawaii. I think they measure it once a month. So here's the actual dates. Sometimes it's nicer to use years since 1900 or years since 2000. Here's the actual amount of carbon dioxide in the atmosphere. And people say that the amount of carbon dioxide in the atmosphere back before the Industrial Revolution was about 280. So if we subtract 280 from all these, we get the kind of excess CO2 above what it was. And that's what I plotted here. And I fitted a good trend line to it. It seems to be increasing exponentially. And we might wonder, what is the derivative of this? But also accounting for the shift from 280 and the years since 1900 and stuff. So let's write this all out on paper. All right, here's a version of the trend line we just had. The amount of carbon dioxide in the atmosphere in parts per million is 280 plus 9.02. I rounded a little bit, but we'll ignore that for now, times e to the 0.0231 times t minus 1900. So here I'm using t in the kind of years we usually use rather than years since 1900. So this converts it to years since 1900. I wrote 2020 here, but the data set I was using only goes up to 1999, I think. You'd get a slightly different curve if you use the full data set. So what is the derivative? How quickly is the CO2 parts per million increasing? So go ahead and take the derivative there. All right, I have a question for you. Can you simplify before you take the derivative by doing 280 plus 9.02 equals 289.02? Is that a good idea? The answer is not just no, but no. That is a classic thing a lot of people try to do because they've been trained to simplify as much as possible, but this doesn't actually work because the 9.02 has something multiplying it, and the 280 does not have that, so these aren't like terms. You can't combine them. So instead of trying to combine them first, we should just live with them because we can't combine them. Let's write the individual terms. 280 plus 9.02 e to the 0.0231 t minus 1900. And then, so that's our function, the derivative. What's the derivative of 280? 280 is a constant, so the derivative is just 0. Can I say the derivative of 9.02 is also 0? Well, 9.02 is a constant vertical multiplier, so I don't take its derivative, I just copy it. Then what's the derivative of e to the stuff? It's e to the same stuff times the derivative of the stuff. So we'll write the stuff here, t minus 1900 derivative. All right, so then how do we take the derivative of that? Well, we still have a 0 here. We still have the 9.02 here. We have all this is the same. And then how about this? Well, the 0.0231 is just a constant vertical multiplier, so I can copy that as well. And then what's the derivative of t minus 1900? You could just say it's 1, or you could say it's 1 minus 0. Derivative of t is 1, the derivative of 1900 is 0, and we're subtracting them. So that's how we take a derivative of a fairly complicated expression like this, thinking about vertical multiplier rule. Did you notice I didn't need the product rule, even though I was doing a product here, because this was a constant rather than being something that depended on t.